This is a solution for the topic test 2018. Question number 1 states that the fast train known as TGV has scheduled average speed of 216 km per hour. The designer of the track wished to minimize the acceleration acting on the passenger to be limited to 0.05 g. What is the minimum radius of curvature that can be tolerated? So this train here has an acceleration here. Of course, will exert a centripetal acceleration towards the passenger. So what would be the radius that will give the centripetal acceleration to be 0.05 g? So in order to do this question, you can first of all write down the formula. The formula states that the centripetal acceleration is given by v squared over r. Okay, so you're looking for the r here. Is given by v squared over centripetal acceleration. So this question, please remember that the v here always in SI. This 216 km per hour convert to SI. That itself carries a mark. So you have to take this times 1000 divided by 3.6. Sorry, not 3.6, 3600. Okay, 3600, and then you have to square the whole term. That's how you change the kilometer per hour into SI unit. And then you have to divide by the centripetal acceleration, which is 0.05 times 9.8. Okay, the answer for this is 7.35 power of 3 meter. Okay, so this is how you should write it always. So I move on to the next question. Next question states that an electron projected horizontally with a speed of 3 to the power 6 meter per second. If the electron traveled 1 meter horizontally, how far did it fall? So recognize this is a projectile motion. Yeah, you have an electron. Perhaps you first of all, electron project horizontally, but we do know that it will go down. Yeah, it will go down because you have a force of gravity. So the question says, if able to travel 1 meter horizontally, how much will it fall? So in order to do this question, first of all, find the time required to travel 1 meter horizontally. In order to do that, this is the formula. So horizontally is 1 meter, and the speed is 3 to the power 6 minus, 3 to the power 6. This is a speed. To find the time here, the time is equals to about 3.33 to the minus 7 seconds. Okay, and from here you can use another equation from the projectile, namely Sy equals to Uyt plus half of gt squared. So what you have here is a time here. So in order to do this, ask yourself what is Uy. Uy will be 0 because it's projected horizontally. And the last term here, g is minus 9.8, and you have to plug in the time, 3.33 minus 7 square. So the answer here is negative 5.44 power minus 13 meter. Okay, and preferably if you can write, you will drop 5.44 minus 30 meter below. So this is the answer. On the third question, this is a topic regarding to torque. So I will just ask you to ignore this part here. So I write down ignore because it will not be tested. And from here we will move on to the next question, number 4. So the question reads like this: Jupiter is the largest planet of the solar system, with more mass than all the other planets combined. So important thing, the radius is 11 times larger than the Earth, and has a mass 318 times greater than Earth. Using the information above, determine the gravitational field strength on the surface of Jupiter. So gravitational field strength is given by this formula. Gravitational field strength is G, so it equals to capital G m over r squared. Okay, so you just need to put in the values for the G. And mass here is 318 times of the Earth. So you're gonna take 318 times the mass of the Earth, which is 5.97 to the power of 24. Okay, close the bracket. And divided by the r squared. R here is on the surface. So you have to take 11 times of the radius of Earth. 6.37 to the power of 6. Whole thing square. Often students will forget to square. The answer here is 25.8 Newton per kilo. That is usually the unit we use for gravitational field strength. So that's how you do it. Second question, of course, you rely on the information in A. Imagine you're able to throw 5 kg watermelon 6.5 meter per second, directed at angle 80 degree above a horizontal. Find the maximum vertical height achieved by watermelon. Yeah, ignore any effect of air resistance. Now in this case, it's a projectile, so how do you find the maximum height? Usually this is the best formula, and we will use this. Okay, at the maximum height, your Vy shall be 0. The vertical velocity always 0, so 0 square. Your Uy is 6.5 sine of 80. Please recap on all this. Yeah, sine of 80, that's a Uy, and square the whole term, plus twice of the G. The G here, there's this common mistake that if you put 9.8, it's not right, because that's for Earth. And as for Jupiter, it is answer from the A, which is negative 25.8. Yeah, so it's a negative and it's 25.8, and then followed by the expression Sy. So you have to do the substitution. So I'm going to make things faster a little bit. The maximum height achieved will be 0.794 meter. Alright, so over here is not 9.8 because Jupiter having stronger gravitational attraction. I will move on. Question number 5. A stone thrown from position near the Earth's surface with initial horizontal velocity of 25 meters per second as shown in the diagram. The vertical component of the velocity of stone at position X is 36 meters per second. Yeah? So at X here, the vertical component is 36. Assume air resistance is negligible. Sketch and label vector diagram to show the addition of the horizontal and vertical components of the velocity at the instant you reach point X. So you have to draw the addition. In other words, it's a vector diagram. How do you want to draw it? This is it. There's lack of space here. Perhaps I'm going to draw at the side. So number 1 is that I will draw Vx. Okay, so Vx label. So, oops, it's not 36. We erase this one to make a correction. This is 25 meters per second. Okay, and at point X or so, the vertical component is 36 meters per second. So if I want to draw it, I do know that object is falling down, so the direction is down, and I want to draw it longer than the Vx because Vy, the value wise, is larger. So it's 36 meters per second. So this is what you should draw. And that's not it, then you have to add them up. So add them up and you use the color here. This is the net vector. Yeah. So I write down V vector. So this is the answer for this component. I'm showing the two components and I add them up. Yeah. The direction must be correct. One is towards the right, one is downwards. Okay, I'll move on. Calculate the magnitude and direction of velocity at point X. So if you want to find the magnitude, I think it's pretty simple. Look at the diagram. You can use the Pythagoras theorem. So I'm going to like using one line to finish it here. So Pythagoras theorem, I want to use finding V here. I take Vx square plus Vy square. Yeah. So Vx square plus Vy square. Technically, this is minus 6 square, and I set the whole thing. Magnitude wise is 43.8 meters per second. Okay, so I answer the magnitude. How about the direction? Direction, I can define the angle here. Yeah. Let me use a different color. Perhaps this is theta that I'm looking. So the theta is below the horizontal. How do I want to find theta? I can use inverse of tangent. Yeah, because tangent theta is Vy over Vx. So inverse of tangent is 36 over 25. So number here is 55.2 degree below horizontal. Okay, so that's the direction. Question 6. A rock mass of 20 grams tied to the end of string is revolved in a vertical circular path of radius 1 meter in clockwise direction shown in the diagram below. The stone revolves with uniform speed 5 meters per second. On the diagram above, draw the arrow indicate all external forces acting on the stone when it's at the highest point. At the highest point, inside the diagram itself, draw the arrows. So there are two forces that are acting on it. Force number 1 is none other than the gravity. So I put an arrow here and I will label W. Okay, preferably if you just write out the whole thing, the weight of it, gravity. And the second force that is acting on the rock here is definitely the string here. The string is holding on to the rock here. So another force here, let me use a different color, a blue color. You have to like draw it very near because exactly it's acting on the stone, so it's still downwards. And the other one here is we call tension. So for a string, please do use the word tension. Don't use the word normal. Don't use the word reaction. Okay, for wire or string, use the word tension. It makes a difference. Hence, calculate the amount of tension exerted on string when it's at the highest position. Alright, so in order to do this, you have to form the net force equation properly. So the net force equation here is, first of all, net force here is Fc. Net force here is towards the center, W and T here, W weight, T for tension. They are heading the same direction. These two combines to become the net force. So I write T plus W. And you are required to find the tension. Tension is equals to Fc, subtract your W. So that's what you need to do. You have to form this equation properly. So we move on to do this. Fc is mv squared over r. W always is mg. So you need to like substitute the value one by one. The mass of the stone or rock here, 0.02 kilo. Speed is 5. Okay, it's uniform according to the question, so we follow it. Radius is 1 minus the 20 gram again in SI, the gravity value. So the answer here is 0.304 Newton. If you got it, then you congratulations to you. Okay, question number 7. Okay, question 7 here, the path taken by skier shown in the diagram below. The path includes two sections where the skier move in uniform circular motion. Two paths over here, you can see the two circles here, two circles. So circle number 1, circle number 2, uniform circular motion means the speed constant. Okay, so move on to question what they ask. Point A in the diagram on page 8 is having radius 20 meter. Point B, circular section with radius 40. So A here radius 20, B radius 40. Skier travel at all sections at constant speed. Okay, both sections are constant speed. Determine the magnitude of the ratio centripetal acceleration at A over centripetal acceleration at B. Okay, if you want to do this question, perhaps we can straight away use the formula that we have. Formula is alright, the A is V squared over R. Yeah, so I have to form these two expression. So how I do is I will write down like this: AC centripetal acceleration, comma for capital A, point A, divided by AC centripetal acceleration, comma for point B. So exactly this is referring to this, yeah. So what's AC? AC is V squared over R. So I write down like this. So I write down V and R for point A. I write down like this: V subscript of A square divided by R subscript A, and close the bracket. Okay, so this is the term for the numerator. So I have to divide by another one. So divide by the AC for position B. Basically, it's the same formula, just that I put in subscript B. This is VB square over R subscript B. Okay, so it is divide. If you do some manipulation over here, when you divide, means that you turn this expression in the other way around. This is what you will have. you have VA over VB, the whole thing you can square it, multiplied by RB, you should use the small letter, RB over RA. Okay, so you have to do some manipulation over there, and then you can substitute the value. Okay, I use a different color. VA and VB is the same, so they are both 18. Okay, so 18 over 8 is actually 1 here. And the RB, radius for B is 40, radius for A is 20. So the ratio answer is simple, is 2. Alright, so it's actually pretty easy. Alright, and move on. The diagram on page 8 draw vectors to show relative magnitude and direction of centrifugal force acting at point A and B. So two things, direction and magnitude. So let us go back to the diagram. So draw an arrow for point A and B. Direction, let us concentrate on direction. Please don't do anything funny. Direction always towards the center. Yeah. Let me just draw this first. I want to comment one more thing. Then ask yourself here, at point A or point B, will you have a stronger centripetal acceleration? If you look back at this expression, the expression just now, this expression states that point A here divided point B is that you have a ratio of 2. Okay, so meaning is that at point A here you will have twice as strong here. Centripetal acceleration is twice as strong. Okay, so centripetal acceleration at A is stronger than B by 2 times. So if you want to draw this arrow, make sure you have arrow for A to be longer than B by exactly twice here. So I go back to that question here. When I'm drawing this, actually I'm wrong because I'm drawing B longer than A, which is not true. Okay, so I'm going to modify this because I know it's not correct. Let me erase it. So the answer for this is that, please, perhaps you can first of all draw A towards the center, and then draw one more for B. Yeah? So it's difficult for me to estimate. So, but I want to draw B exactly twice as short. Yeah, perhaps it's this. So remember, arrow for A is twice. Yeah, is twice the arrow for B. Question 8 is where you have a long section or long response here. Question 8 states that the Hubble Space Telescope HST is a low-orbit space telescope launched 1990. It is orbiting Earth with altitude of 548 km under uniform circular motion. HST has a mass 1.11 power 4 kg, capable of collecting infrared, visible light, and ultraviolet images from the space. Find the gravitational force between Earth and HST at its orbiting altitude. Also calculate the acceleration of HST at that moment. So two things. First of all, find the force, then you find the acceleration. So in order to find force, you use the Newton's law, G(m)m over r squared. So nothing much about this here, just that you have to substitute the value. You have to do that here. And mass of Earth, because these are all two things, and the HST here. R, on the other hand, be careful here. R is the distance from center to center. So in this case, you have to consider the radius of the Earth, 6.37 to the power 6 meter. You have to plus the orbiting altitude, 548 kilometer, which means you have to put 3 more zeros. And don't forget to square it. So this is the proper R. So also this is where always a mistake. Either forget to add or you forget that it's kilometer. Answer for this is 9.24 to the power of 4 Newton. So that's the first part. Secondly, find the acceleration. So you want to find acceleration, pretty simple. Just use the normal F equals to ma, because you already have the force. So you have to find A here is equals to F over m. Force acting on HST. So 9.24 power 4 divided by the mass of HST. The answer for this is 8.32 ms minus 2. Okay, so this is the answer for both parts. The second question asks you about this. Hence or otherwise, calculate the linear speed of HST at the same altitude. What is the speed? Yeah, if you have the acceleration already. One way of doing is by relating these two formula. If I want to find the speed, I have to take r multiplied by centripetal acceleration divided by the third of it. So in order to do this, v equals to r. R again is the tricky part. Make sure you write down everything. Plus 548, 3 zeros. Yeah, and you have to multiply by centripetal acceleration, which is the 8.32 from previous calculation. And don't forget to square root the entire term. The answer is 7.59 power of 3 meter per second. Okay, remember all satellites are traveling at high speed. Yeah, so this is very common. You get anything smaller, please do check again your working. Move on. The orbital period show that it is approximately 95.5 minutes. So what you can do, you perhaps can use the circular motion formula. From the speed here, I can calculate the period. Is 2 pi r over the v. So I put in over here. R again is the tricky one. It's a long term, but I still have to write it down. Okay, divided by the speed just calculated to be this value. The answer here that I have here, use your calculator. This is in SI unit. So if you want to like follow the question here, show that it's in minutes, I'll leave it for you to do. I'm pretty sure you know how to convert. So it is approximately, I'll use this sign here, approximately 95.5 minutes. Yeah, so just do it slowly, carefully. Now we'll move on. I think there's one more question. Okay. Alright, determine the number of times HST orbits the Earth in a day. Give your answer to the nearest whole number. This is quite simple. Yeah. So number of orbits here. Number of orbits. So one day you have 24 hours times 60 minutes in every hour. Alright, and you divide by the time. The orbital period is 95.5 here. So you get the number is 15.08 times. Okay, there's a jump over here. I do not know why. Let me move back to the question. Alright, go back. Okay, this is not your final answer because the nearest whole number 15 times. So that's the first part of the long question. I will move to question number 10. Timothy is a long jumper athlete, mass of 65 kilo, who is capable of leaping with initial velocity 11 meters per second, 40 degrees above horizontal. The jump model can be modeled as projectile motion with negligible air resistance. Determine the vertical component of the initial velocity. This part, I don't think you have much problem. You have problem over here, you better do something. Alright, so this 11 sine of 40 degree, 7.07 meter per second. And the second part, horizontal part, ux is u cosine of theta. Again, you cannot afford not knowing this. So this is 8.43 here. So the two answers that we want is 7.07 and 8.43. And find the time of flight, Timothy, given that he lands at the same level as he jumped. What's the time of flight? For this part, there are several ways of doing, but I'm going to show only one way. I will use my usual method, which is this formula. You can use other formula as long as it's correct. So I'm going to use my argument. When he lands on the same ground, the SY is 0 because he does not gain any vertical displacement. Uy is 7.07 followed by t. half of gt squared. G is negative 9.8, so it will make it fast is minus 4.9 t squared. What I can do next is factorize the t. Okay, so one answer, t0 definitely is not the one that we want. Yeah, the answer is 7.07 divided by 4.9. This is the answer that we want, 1.44 seconds. Right, and then determine the range of his jump. Range here, there's only one formula, don't try anything else. Ux is 8.43, determined earlier. The time of flight 1.44. Answer 12.1 meter. Yeah, actually this number is ridiculous. It's more than the world record. Never mind. I'll move on. This is the toughest here. Find the kinetic energy of Timothy at the moment he completed 3/4 of the jump. 3/4 of the jump, yeah, meaning that we're going to take time here to be 3/4 of the time of flight, which is 1.44. At this moment, yeah, 1.08 seconds, what is the kinetic energy? So one way of doing is by using or finding the V. So I do know that Vx is always 8.43 meter per second. Okay, so what I can do next is find my Vy. Yeah, so Vy, one of the method is by using this formula. Okay, Uy is 7.07 plus negative 9.8, followed by the time that we are interested, 1.08. This value here is negative 3.51, which means that fella is descending. So with this knowledge of Vx and Vy, I can combine them using a Pythagoras theorem. So let me draw a line here, running out space. I do over here, yeah. So I can do this. V squared equals to Vx squared plus Vy squared. Pythagoras theorem. And I want to find kinetic energy is half mv squared. Correct? Okay, so kinetic energy. Okay, so I forget to write this now. Kinetic energy is half mv squared, half m, mass of Timothy 65. What is the v squared? V squared is Vx squared plus Vy squared. So Vx squared is 8.43 square plus the Vy is negative 3.51 term square and then close the whole bracket. Okay, so look carefully around this, running out of space, so I need your attention to do it yourself. This is 2.71 to the power of 3 joule. So I've given you the answer, you can slowly work towards it. This is the final question, question number 11. Astronomers have discovered a planet mass m that moves in circular orbit radius r, 5.24 power of 10 meter, about a star of mass capital M as shown in the diagram. The planet has orbital period of 132 Earth days. The mass of planet 8.90 power 25 kilogram. Using Newton's law of universal gravitation, Newton's second law of motion show that the capital M, yeah, mass of star is given by the term here. Basically deriving this the Kepler's third law. Okay, so they have to show it. This is the answer. Show it out here. So you want to do this is that using the two formula, the two equation here. Universal gravitation meaning Fg. So it's equals to Fc. Because centripetal force of this planet is given by the gravitational force. So we're going to expand this formula left and right. Simplify a little bit, use different color. R here you can reduce one of the power. Small m you can cut. You do so, this is what you will get. Okay, of course still far away from the full form here. So you have to expand the V. That is the part that you have to be careful. V here is 2 pi r over the period. Don't forget that this whole thing is actually square. So expand this term once again. You have on the right hand side 4 pi square r square over t square. Now you need to make capital M as your subject. So I'm pretty sure you can rearrange this, make M as subject, equals to r equal to the right hand side becomes r cubed. Yeah, r squared with r combined, r cubed. And at the bottom here, what happened is that g, you have to go to the right hand side, put at the bottom here is g and t squared. So this is the form that we want. And how do you start? Make fc equals to fg and you expand. And v here also you have to expand. Okay, from A, I'll go for question B. Calculate the mass m of the star. So I have the formula. What I can do now is substitute the number slowly here. So start one by one. So 4 pi squared is a constant. No need to worry about that. On the r here, from question it's given. Okay, something missing. Let me rewrite. Capital M equals to 4 pi squared. R is given by the question 5.24 to the power of 10. Cube this thing. Yeah. Students always forget. Divide by gt squared. G, capital G is a constant. The t here, be careful, is in SI, so 132 Earth days. So change the days to seconds. 24 hours a day times 3,600 seconds an hour. Okay, so in this part again, the square here is the killer. The answer here is 6.55 to the power of 29 kilogram. So one tips here, mass of the star is huge. So this number is similar to the sun. Your answer is pretty much reasonable, yeah, or logical. Okay, and from here, I think we move to the last section already. But this thing just refused to move. Oh, God. Need a moment. Just now program not responding. Never mind, last one. The planet M is known to rotate around its axis once every 2.45 Earth days. Rotate around its axis, yeah, every 2.45 Earth days. If an artificial geostationary satellite were to orbit planet M, what is its orbital radius? Okay, so what's the orbital radius for this satellite, geostationary satellite? Any satellite, you can always use the Kepler's law to describe it. So I'm going to find the orbital radius, meaning I'm finding the r. So Kepler's law that we had just now. This is the formula. Yeah. So I'm looking for orbital radius, meaning the r. So do I have sufficient info? I will have here if I do know the t. So in this case, I really have enough information. I just need to put in carefully. The mass here is the mass of the planet. Yeah, it's not mass of the star, because this is the planet satellite system. Alright, and the mass of the planet, according to the question, is given earlier. And what is the period here is for this particular planet is 2.45 Earth days. So I'm going to write, you have to multiply by 2.45, again change to SI unit, close the bracket, square the whole thing, divided by 4 pi squared. Okay, so this is the whole expression for r cubed. And if I only want r, then I can do something like this. Yeah. So if I only want r, meaning I have to take this whole thing and you cube root it. Fast way of writing is 1/3 of the power. This is how you express cube root. The answer immediately will appear 1.8 to the power of 8 meter. Okay, so I think that's all for the solutions. Try your best and you have to attempt the questions. Good luck.